8, 7, 6, 5. Blast off. Okay, we're back on the air. So the first thing is, if I remember right, we went through the code. Everything was explained for homework 1. And did I say it was due today, or give it due date? Or did I say when it was due? 2 weeks. 2 weeks. From when? Okay, so how many people are working on it or have done it, or any questions about it? Should be straightforward, right? Easy. Am I right? Okay, so there are no questions about that. Okay. All right, so now what I want to do is a review. So I want to review the stuff from the Stochastic Models course, the prerequisite material you're supposed to know. For some of you, this may be boring because you just had it in Stochastic Models. For some of you, even though you may have just had it, it still might be a worthwhile review. Others of you may not have had it because you may have taken your probability someplace else, and maybe this surely would know some of this. But anyhow, if this turns out to be boring, sorry about that, but I think it's probably better to be boring and clear, not leave anybody behind, than to try and be efficient and leave people behind. So what I'd like you to do is download, and I have a copy here, but for next time, what I'm doing is I'm going to look at homework 0 from the Stochastic Models course, which is sort of the calculus review as a prerequisite for that course, except that when I do it in that course, it's just a calculus lecture and really has nothing to do with probability. But now, if you've had probability, now I can sort of do both at the same time. So look back on your homework 0. Now, the way you get this is go to the course website, and you'll see that there are several courses listed there. This course is the Stochastic Models course, STA 4821, and it's homework 0. So download homework 0 from the Stochastic Models course. Okay, but here it is. And as I say, for those of you who took Stochastic Models, you've already done this homework, except that when you did it, it was with different parameter values, but that doesn't matter. Okay, so this is a homework 0 mathematics review for the previous course, the Stochastic Models prerequisite. And it says on the paper that the purpose is to review topics from calculus that will be useful in the Stochastic Models course. But I want to use this as a basis for giving a review of stochastic models in general. So we start off with the idea of a random variable. And a random variable corresponds to performing some kind of experiment in which there's a numerical outcome. A typical example would be rolling dice, or spinning a dial, let's say, that points to a number. Or I could say toss a coin. If I tossed a coin and I wrote a number for head and a number for tail, then that would be in a random variable form. So I could say, if you get a head, call that a 1. If you get a tail, call that a 2, for example. And then the value that you get when you perform that experiment, that would be a random variable. Now, in general, random variable is defined by one of two different functions, or there are two different functions. Let's see, we got to have one of these things that writes. Okay, there's the density function, and there's the distribution function. Now, discrete random variables, like that is random variables that take values in a countable set, like, for example, rolling dice, they don't have a density function, they have a probability mass function. Every kind of random variable has a distribution function. But for continuous random variables, those that have a density function, the relationship is as follows. The density function is the derivative of the distribution function. And the distribution function, what it means, by the way, the distribution function physically means the probability that the random variable is less than or equal to t. So in this notation for a distribution function, okay, let me write that down. This is called distribution function. And the conventional notation is you use a capital F to represent distribution function. The t is the argument, and x is the name of the random variable in question. So this then represents the probability that the random variable x takes a value less than or equal to t. And if you know this function for all values of t, then that is all the information there is about the random variable. That contains all the information. Now, the density function is a function whose areas represent probabilities. And that's the fundamental theorem of calculus. That's the relationship between the two. Because if I know the distribution function, I get the density function by differentiation. So therefore, if I know the density function, I can get the distribution function by integration. So here is the area under the density function curve between minus infinity and t. And then that is the probability that x is less than or equal to t. This is a definite integral, and the relationship between these two things, that's the fundamental theorem of calculus. And a lot of undergraduates have trouble with this because they don't really understand the relationship between derivatives and integrals, as that is, they don't understand the notion of a definite integral. They only know a indefinite integral, which by definition is the inverse of the derivative. And the fundamental theorem of calculus says that those things are areas. So in our case, and what homework 0 asks you to do for some special cases is I give you the little f, and I ask you to calculate the big F by evaluating this integral. And so you have to just follow the rules of calculus and remember that this is a definite integral, not an indefinite integral. If it's an indefinite integral, that means that there's an answer plus some constant, the arbitrary constant. And if you don't specify that constant, then unless the constant happens to be 0, you're going to get the wrong answer. So this is the way you should look at it. Now, if I have a random variable, and it's defined by either or both the density function or the distribution function, then there are certain characteristics I can calculate. The first one is called the first moment, or expected value. And by definition, that's equal to the integral over all t of t times the density function evaluated at t dt. So in effect, this piece right here represents the probability that x is equal to t, except that with a continuous random variable, one that has a density function, the probability that x equals any specific value is 0. But what this says is that I interpret the density function times dt, that's sort of a strip of area, of infinitesimal width. And what I'm doing with this integral is I am multiplying the area of that infinitesimal width, with the area of that strip of infinitesimal width, which of course is 0. I'm going to multiply that probability then that x lies between t and t plus dt by the value t. So I'm weighting the values the random variable takes by the probability that it takes those values and adding them up. And then that gives me the expected value or the mean value. Now, I'm doing this pretty fast if you've never seen this before, but if you have seen it before, then this should all ring a bell, and you should understand what I'm talking about. And if there's any questions, like you don't understand what I'm talking about, just raise your hand and ask so we get that out of the way. Because the whole idea here is to review something, and if I'm reviewing it but it's not a review, doesn't make any sense, then I'm wasting time. So let me know if there's any question about what I mean here when I write these things down. Okay, now the second thing I want to define is what's called the second moment. It's the average or expected value of the square of the random variable. And that's obtained by weighting the square of the values the random variable takes by the probability that it takes that value. And then adding them up over all t, that is between minus and plus infinity. And it turns out that this second moment is important in describing the amount of variability or the variance of a random variable. The variance, if you remember, I call it capital V of x as an analogy with E of x. Most people write it VAR, var of x. There's a theorem that says that that's equal to the average of the square minus the square of the average. That's not its definition, that's a theorem. But in any event, this is a measure of how variable the random variable is. So the expected value is sort of a central location, and the variance is a measure of how much the random variable bounces around that central value or that average value. Then there's something called convolution, which causes lots of grief in the undergraduate course, but actually won't be as important in this course. But I'll write it down. Now, the convolution is defined this way. I'm calling it g of t, and it's equal to the integral between minus and plus infinity of the density function of the random variable evaluated at u times the density function evaluated at t minus u du. The meaning of this is that if I have two independent random variables with density functions, in general this is f of x1 and this is f of x2, but in our applications they're almost always two random variables that come from the same population. So what this says is that if I add two random variables or two realizations of two independent realizations of a single random variable whose density function is f, little f, then this integral gives me the density function of the sum of those random variables. So an example, except it's discrete. This is, remember, for continuous random variables. But an example might be if I have two dice, then each die could be viewed as a random variable, which takes the values 1 through 6. And if I have two of them and I roll them and then I add them up, then I'm interested in the sum of the two dice, and that would be calculated by a convolution, except that there the things I would be adding up, because remember integral means sum, the things I would be adding up would be probabilities, not density functions, and the result would be a probability, not a density function. But this will not be especially important for the queuing theory course, which I could see causes some relief there. But it's an important concept because we will be adding up random variables in the course. For example, if you look at a queue in which a customer arrives and he has to wait in the queue, the length of time that he waits is the sum of the service times of the customers in front of him in the queue. Now, we're going to solve that problem, but we're not going to do it by formally calculating convolutions, but the concept is the same. I'm just going to figure out a better way to calculate convolution for our particular application. Okay, then what it does in the homework problem is it asks you to evaluate some of these things for two particular cases. Now, as they're given in the homework problem, they're just arbitrary functions, but I want to look at them. I think I'll erase this part here. They're important density functions. They describe important random variables. They'll be important in this course, so it's worthwhile looking at where those things come from. So the first case gives this as a density function. It says the density function is equal to 0 if t is negative, is equal to 1 if t lies between 0 and 1, and is equal to 0 if t is greater than 1. Okay. So if you draw a graph of that, looks like this. There's the density function. There's the argument. Here's 0. Here's 1. Here's 1. So drawing the graph of this, I get 0, that's this branch, then 1, that's this branch, and then 0 again. So that's what the density function, that's what this density function looks like. Okay, now, question here is, what does that represent? And the answer is, well, I want to make a model of the following idea. So there are zillions of density functions. Remember, in fact, the only requirement for a function to be a density function is that it can never be negative and its total area has to be 1. So I'm looking here at a specific density function. Obviously, it's never negative and its total area is 1. What this is supposed to model is the following idea. I have this circle with a little arrow, like a child's game, and I flick the arrow, and it's going to pick out a point on the circumference of the circle, which is 1, a point between 0 and 1. Or equivalently, what I'm going to do is I'm going to imagine that I have this interval, 0 to 1, and I pick a point at random. And when I say at random, what I mean here is I want to model the idea that every point on the circumference of the circle, every point in this interval, is equally likely to be chosen. Okay, so what does that mean? Well, one way to look at it is to say, well, the probability of each of those points is the same. But what would the probability be? Well, under the ordinary intuitive notion of elementary probability, if a random variable can take a certain number of values and they're all supposed to be equally likely, then what I would do is I would count how many values there are, and let's say there are n of them, and I would assign each one the probability 1 over n. Did you have a question? No, okay. I would assign each one the probability 1 over n. So imagine here that there are n points, and I assign each one of them the probability 1 over n. But of course, there aren't n points. There's an uncountably infinite number of points. So I could take the viewpoint that I could take this interval, and I could divide it up into little tiny subintervals. And if there are n of those, then the probability that I fall in any particular one of them would be 1 over n. And then I let n go to infinity, pass from discrete to continuous time here. And then, of course, the probability of each one of them would be 0. So that's the general difficulty that students have with undergraduate probability with continuous random variables, is that, as this example indicates, if you could take an uncountably infinite number of values, then in general the probability of any specific value is 0. So the probability that I get any particular value is 0, but of course at any time I perform the experiment I have to get some value. So how am I going to describe this? And the answer is, well, I'm going to describe it by means of its distribution function. Okay, so here's the distribution function. The distribution function represents the probability, and I'll draw a graph here. Okay, so here is a distribution function, capital F of t, and this is a probability. Remember, the density function is not a probability. The areas under the density functions are probabilities. So the density function by itself is not a probability. The distribution function is a probability. By definition, it's the probability that the random variable value is less than or equal to t. And of course, you could see that what that means is that since it's a probability, its values all lie between 0 and 1, and when t is minus infinity, this value must be 0. When t is plus infinity, that value must be 1. And in between, it must be non-decreasing. That is, as I move from left to right, the probability that x is less than or equal to t, as t gets bigger, that probability cannot get smaller. It could remain the same, or it could get larger. Okay, now I want to find the distribution function for this particular experiment. So the argument goes like this. I say, well, first of all, what's capital F of t when t is negative? Obviously, if t is a negative number, the probability that x will be less than or equal to that is 0, because all my values must lie between 0 and 1. So capital F is going to be 0 when t is negative. Similarly, what's the probability that x is less than or equal to t if t is greater than 1? And the answer is, well, since whenever I spin the dial, I have to get a number between 0 and 1, the probability that x is less than or equal to a number that's bigger than 1 must be 100%. It'll always be less than a number bigger than 1. So capital F is 1 if t is greater than 1. Now, suppose that we're looking at a value of t that lies between 0 and 1. And then you could say, well, let's say, for example, what's the probability that when I spin this dial, I'll get a value less than 1/2? You say, well, obviously, if I'm supposed to have, modeling the idea that all points are equally likely, then since half the points lie here and half the points lie here, then the probability that I lie here, or less than or equal to 1/2, must be 1/2. Half the time I'll lie in this interval. In fact, if this were, say, 3/4, and I asked for capital F of 3/4, then the probability that when I spin the dial, the arrow would lie between 0 and 3/4 should be 3/4, 0.75, because 75% of the points in this common sense view are going to lie between 0 and 0.75. So in other words, F of 1/2 equals 1/2, F of 3/4 equals 3/4, F of t equals t. So there's my distribution function, and that's derived from this intuitive model, because this is supposed to be describing this idea of flicking this arrow. So if I draw the graph of this, I see I get 0 for t negative, and here's the value 1. And then between 0 and 1, the function is f of t equals t, so it looks like that. And then after that, the function is 1. So this fits the criteria for a distribution function. It's minus infinity. At minus infinity, it's 0. At plus infinity, it's 1. And it never decreases. So it's a distribution function. Now, let's look at the relationship between these two, because I started out with this, and I said that this was the density function for this experiment, but I didn't say why. I just said it was. This is the distribution function for this experiment because I derived it using this model. That was a physical argument. Now, notice that these two, little f and big F, obey these particular definitions. Little f is a derivative of big F. Let's see if that's true. Well, the derivative of 0 is 0. The derivative of t is 1. The derivative of 1 is 0. So yes, in this example, if I differentiate big F, then I get the little f. So therefore, this must be the density function associated with this experiment, because it comes from the distribution function associated with that experiment. Okay, what about going the other way around? So now I want to show that big F is the area under the little f curve between minus infinity and t. So you can imagine that if I had a vertical line here at some value t, that the height of the lower graph is equal to the cumulative area to the left of that value for the upper graph. In other words, as I move my argument from left to right, the cumulative area and the upper graph is the height, or is represented by the lower graph. So if my t is negative, then the area to the left of that negative value is 0. If my t is bigger than 1, then the area to the left of that value of t is all of this area, which is 100%. For a t between 0 and 1, the area to the left of t is just the area under that rectangle, whose area is t. So this graph, for each value of t, the height of that graph represents the area to the left of that point and the graph above it. So that means that the lower graph is the integral of the upper graph. So in other words, these conditions are met. So what we did here is we looked at a particular kind of physical model, namely going to spin this dial. I'm going to pick out a point between 0 and 1, and all points are supposed to be equally likely. That's our physical model. And then from that, I get this distribution function. So this was obtained by this physical argument. And then from that, I get the density function by differentiating. And if I have the density function by differentiating, then if I started with that density function, I could go backwards and get the distribution function by integrating. So little f and big F are equivalent, and this is a special case. All right, now, for this particular case, a random variable that is described by this density function and this distribution function is said to be uniformly distributed. So we say x is distributed as, you use a little squiggle there, as, this is conventional notation, a uniform variable with parameters 0 and 1. This is the standard case, the 0 and 1, but in general you could have a uniform distribution between any two values. Okay? So we say x is uniform between 0 and 1. So this is a uniform random variable. Now it turns out that this is a model for the random number generator in a computer. So when you want to do simulations, then, and we'll be doing this, when you ask the computer to generate a random number, what it does in effect is it has a deterministic algorithm that generates a string of numbers which, although they're deterministic, they appear. That's why it's called actually it's a pseudo-random number generator. That string of numbers appears to be generated by spinning this dial. So the random number generator generates uniform random variable values, and from that we're going to translate that into random variable values that correspond to any density or distribution function. So for example, in our queuing problems, if we want to simulate, as you did in your homework, in homework 1, you simulated a case in which the inter-arrival times were exponentially distributed, whatever that means. We'll get to that in a moment. And what you did was I gave you an instruction whereby you would invoke the random number generator, which would generate a number whose density function is this. And then that is plugged into a formula, a logarithm formula, which distorts that value. And when it does distort it, it changes it to another random number. And as we'll show later, that random number turns out to be exponentially distributed. So we've got to discuss what we mean by an exponential distribution, and in fact what we mean in general by using the computer's random number generator to generate values that have any specified distribution or density function. And that's always done by what's called the inverse transform method. I shouldn't say always done, but in our course it's always done that way. So what we'll do is we'll invoke the random number generator, and it will be generating numbers whose distribution function is this, which means it's doing the equivalent of spinning this dial, and then it'll take those numbers and turn them into other numbers which will have whatever distribution function it is we want. That's what the inverse transform method does. That's what you did in homework 1, although I didn't explain it. I just gave you the code so you could run it, and so the explanation is coming soon. Okay, so that's the uniform. Now, if you were to take the homework 0 in the stochastic models course and calculate the expected value, what's the expected value of x in this case? Well, you take the values the random variable takes times the probability it takes those values. That's this. And then you sum them up over all possible values. So in this particular case, since little f is 0 when t is outside the interval 0, 1, that means that I don't have to worry about those values. So I can reduce this integral to values between 0 and 1, because between minus infinity and 0 and 1 and plus infinity, that function is 0 by definition. In that interval, that function is 1. So the expected value would be t times 1 dt. And then, of course, it's easy to evaluate that, and that turns out to be equal to 1/2. Okay, now, with that one half is intuitively obvious, I think, because remember, if what we're doing here is we're generating numbers that lie between 0 and 1, and we do that in such a way that every point on this interval is equally likely to be selected, then you would expect that the value to the left of one half and the value to the right of one half would balance each other, and that the long run average would be exactly in the middle, one half, and that's what this thing predicts. And in the stochastic models class, part of the course is that after making this argument, then we simulate this and then see that in fact the theory and the experiment agree. If I wanted to calculate the second moment, then I would evaluate the integral from 0 to 1 of t squared dt. So that would become t cubed over 3 when I integrate it between 0 and 1, and that's 1/3. So the variance of a uniform random variable by our earlier formula is the second moment minus the square of the first moment. So the second moment is 1/3, and the first moment is 1/2, and I square that. 1/3 minus 1/4 is 1/12. That's the variance of a uniform random variable between 0 and 1. Okay, so this is a quick review of homework 0. First part of homework 0, stochastic models course. So everybody this should ring a bell with everybody. Are there any questions about this? Is it straightforward, or any doubts or little points you need cleared up? Okay, that was the uniform. Now the second one that's investigated here is what's called the exponential. Okay, so let me erase this. So in this case, we say that the random variable, x, is what I'm calling it, is distributed according to the exponential distribution. So I write exp, and there's a parameter which is conventionally called lambda. And so that's exponential. And that also turns out to be very important in all kinds of applications, especially in queuing theory. All right, now here is the definition of the density function for the exponential. Density function is equal to 0 if t is negative, and lambda e to the minus lambda t if t is not negative, where lambda is a positive constant. Okay, so first thing I want to do, well, let me draw the graph of that so I make the argument in the same order as I made it over here. Okay, so what does the graph look like? Here's t. Here's the density function evaluated at t. And in stochastic models course, the students are asked to draw these graphs. So the graph is equal to 0 when t is negative, and then as you pass the origin, you jump from this branch to that branch. And so when t is equal to 0, this has the value lambda, and then it decays exponentially like that, and is asymptotic to 0. Okay, now it'll turn out that this represents the physical model of events, times between events occurring randomly in time. The typical example that is given on the textbooks is a Geiger counter. So with a Geiger counter, what you have is you have these radioactive particles which are decaying. And every once in a while you hear click, 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 and so forth. And the question is, if these particles decay at random, how much time elapses between clicks? So you could say, well, here's a click, and there's a click, and then there's one, and there's one, and there's one, and so on. So this interval would be x1, that interval would be x2, x3, and so forth. Okay, now I want to describe what that is. So what I'm going to do is the same kind of argument I made before. I'm going to find the distribution function through a physical argument and then differentiate it to get a density function. Okay, so let me find the distribution function. And so let's see, I need some space. So I think I'll erase this. And I'll do it right here. So here's the argument. Now, in queuing theory, typically the exponential distribution is used to describe the times between arrivals. So whereas the arrows that I just drew here and erased, whereas they represented clicks in a Geiger counter, in our application, those arrows will represent the instance at which customers arrive and request service. So we have a random arrival process in which statistically speaking, the times between arrivals are just the same as the times between clicks in the Geiger counter. Okay, so I want to make a model just like that one that will lead to that. So here's the argument. Here's 0. Here's some time t. And I want to calculate the probability that x is greater than t. Now, the distribution function, by definition, is the probability that x is less than or equal to t, but that's just a convention. So I'm going to calculate greater than because that's more convenient and recognize that the probability that x is greater than is 1 minus the probability that it's less than t, or in other words, it's 1 minus the distribution function. So what I'm calculating is not the distribution function, but I have to subtract from 1 to get the distribution function. Now, notice, by the way, I'm going to assume here that t is greater than or equal to 0. Because it's obvious physically that if t is negative, the probability that x is less than or equal to a negative value will be 0, since the only values that are allowed are non-negative values. So it's the same argument as before. So what we're doing here is we're presuming that we have this random selection, these random arrivals in time, and we want to calculate the probability that the time I have to wait from now until my next arrival or my next click is longer than t. So in other words, that the first arrow that I get is going to be to the right of t. So the way I'm going to make that argument is I'll say, okay, what I'll do is I'll divide time up into little intervals. So I'm going to make time discrete. Okay, now I'm going to go over this. This will come up again later in the course. So all of this details will be filled in later because I'm going to attack this through different ways because it turns out that this is a critical factor in the mathematical analysis of queues. So the way I'm handling it is I'm going to imagine that time is divided up into little intervals, and then I'm going to make some assumptions in my model. The first assumption is that every interval of equal length has the same probability of having an arrow as every other one. In other words, you're just as likely to have an arrow at any point in time as you are at any other point in time. And it doesn't depend on the absolute value of the time. So in a sense, it's just like the uniform, except that in the case of the uniform, the points were required to lie between 0 and 1. And in this case, you have a half-infinite interval. Okay, so every interval of equal length has the same probability of having an arrow as every other interval of equal length. Now, we want these times at which the arrows can occur to be continuous. We want to have a continuous random variable here. So the strategy is going to be that we first assume, just like before, that time is discrete, and then we'll write some expression, and then we'll take the limit as the width of those little intervals goes to 0, so they become points. So the first assumption is that every interval of equal length has the same probability of having an arrow, and let's call that probability little p. Furthermore, these intervals are independent of each other. This is a critical assumption now. So I'm assuming, because this makes perfect sense from our physical model, that whether or not I have an arrival in this interval, or a Geiger counter click, whether or not I have an arrival in any interval does not affect the probability of having an arrival in any other interval. So each interval is like an independent trial. So each instant in time, God tosses a coin, and if it comes up heads, he makes the Geiger counter click. And if it comes up tails, he doesn't make it click. So we have these independent trials. And finally, I'm going to assume that there is a stable arrival rate at which these arrows occur. In other words, I'm assuming that although this is a random process and the arrows are unpredictable in the short run, in the long run, I could say that they're going to arrive at some rate, which I'm going to call lambda. So lambda is the arrival rate. So what that means is that the way I would calculate lambda is I would count over a long period of time how many arrivals occur, divide that by the length of time, that gives me arrivals per unit time, or clicks per unit time. And that should be stable. In other words, after I've done it for a long period of time, if I continue to do it, then the value of lambda remains the same. It doesn't vary in little intervals or in big intervals. It's a stable arrival rate. So those are my assumptions, and they're not very restrictive. Like lots of things are going to fit that model. So let's say, what is this probability then? So first of all, I'll say, well, the probability that x is greater than t, that means that there's no arrow in the first interval and no arrow in the second interval, and so forth. So that means that the probability of no arrow in the first interval, if p is the probability of an arrow, 1 minus p is the probability of no arrow. The probability of no arrow in the second little interval is also 1 minus p. So if the intervals are independent of each other, the probability of no arrow in the first two intervals is 1 minus p quantity squared. And first three intervals, 1 minus p cubed, and so forth. So if I have n intervals, if that's interval number 1 and that's interval number n, then the probability that I have no arrow in the first n intervals is 1 minus p to the nth power. So the 1 minus p is because all the intervals are of equal length and therefore have the same probability of having an arrow or not. And the raised to the nth power is because the little intervals are independent of each other. Okay, now I want to take the limit of this as n goes to infinity, because right now I have a discrete process, and what I want to do is, if I let n go to infinity, that means that if I have an infinite number of little intervals of equal length between 0 and t, then each of those intervals goes to a point. And so this should be equal to the limit as n goes to infinity of 1 minus p to the nth power. Now, all of the intelligence is there. Well, I still have a couple of more things to say, but let me step back a minute. This thing here says that I'm going to let the intervals go to points. Okay. Now, in order to take this limit, I need to write down a couple of other conditions. The first thing is that the value of p should go to 0. Okay, now why is that? Because p is the probability of having an arrow in an interval, and if the interval's length goes to 0, then the probability of having an arrow at exactly one specific point should be 0. In other words, if I have an infinite number, uncountably infinite number of points, all of which are equally likely to have an arrow, the probability that any specific point has an arrow must be 0, just as it was over here. Same argument. So as the interval width goes to 0, the probability that it contains an arrow goes to 0. But the arrows, remember this p is just a mathematical fiction, but we're assuming that in the real process, if we measure things, that the rate at which the arrows occur is is a constant. So now I'm going to relate n and p so that I can take this limit. Okay, so n goes to infinity and p goes to 0, but on average, how many arrows would I expect to get? And I claim that the average number of arrows I would expect to get is np. Okay, why is that? Well, I have n intervals or n trials, and each trial has an arrow with probability p, which means the frequency of intervals that have arrows is p. So as n gets bigger and p gets smaller, np, which is the average number, should remain the same. In other words, if I toss a coin 100 times and the probability of getting a head on any trial is 1/2, how many heads would I expect to get? 100 times 1/2, or 50 heads. So np is the expected number of arrows that I would get between 0 and t. And now I'm going to let n get bigger and p get smaller, but I'm going to keep np constant because the expected number of arrows just depends on the real process and not on its mathematical model. Okay, so I'm going to set np equal to lambda t. Why lambda t? Well, by definition, lambda is the rate at which the arrows occur, arrows per unit time. So if I multiply the rate times the time, I would get the number of arrows. So I set the product np equal to lambda and t, which are in principle measurable. I can measure lambda, that's one of our assumptions, and t is just whatever value I pick, so that what I'm doing is I'm going to take the limit as n goes to infinity, p goes to 0, but constraining the product to remain constant with a value lambda t. And that's my intelligence. That's my model, and the rest of it's arithmetic. So here's the arithmetic. The first thing I do is rewrite this as the limit as n goes to infinity, and I replace p from this equation here by lambda t over n. So now this is a more accessible form. I want to take the limit as n goes to infinity of 1 minus lambda t over n to the n. Okay, now let me remind you of a theorem. So this is a standard theorem in analysis. You usually learn something like this in advanced calculus or some course like that. And the theorem says, and you might very well know this, that the limit of 1 plus x over n to the n as n goes to infinity is what? Anybody know? E to the x. In fact, in some developments of mathematics, you could take this as the definition of the exponential. Turns out this is true whether x is positive or negative. Now, this may be a sophisticated theorem to prove, but that's irrelevant for us because this is just a mathematical fact. So we accept this fact, and that means that when I take this limit over here, it's e to the minus lambda t, because the minus lambda t plays the role of x. So I have derived the fact that for t positive, 1 minus its distribution function is equal to e to the minus lambda t. So that means that the distribution function of x evaluated at t is equal to 0 if t is negative, and is 1 minus e to the minus lambda t if t is not negative. So it's really amazing when you think about it that here we have a model that's describes lots of things in nature. It describes, well, let's see. It describes clicks on a Geiger counter. You could say it describes messages arriving at a node in the internet for transmission someplace else, and that is an arrival processing queues. The times between arrows could be the times between, let's say, you might sit there at a portion of I-95, and every time a crash occurs, that's an arrow. And the times separating successive arrows should be approximated by an exponential distribution, because you could say that the probability of a crash at any little time interval is just like any other little time interval, and they're independent of each other pretty much. And so we have the exponential distribution then that describes the times between crashes. It describes the times between arrivals of messages. It describes the times between instance of radioactive decay. So it describes all kinds of things. In fact, one example I like to give to show the relationship between the sublime and the ridiculous is, on the one hand, we could say that this describes the physics of fundamental particles. That was our original example. But here's another one. Suppose that instead of using time as my dimension, I call it distance. And I imagine that I have a cow path. And cows walk along this path, and they drop their patties. And so there's one, and there's one, and there's one, and so forth. And you can say, well, when a cow drops its patty, it's just as likely to drop it in one place as any other place. Doesn't care. And it's independent of what the other cows are doing. It doesn't care. So therefore, except for the fact that now, instead of talking about the times between arrows, I'm talking about the distance between arrows. But it should follow the same rules. So the rules that describe the behavior of fundamental particles and the rules that describe cows dropping their patties, same thing. Yes? No, wait, this means if we're talking about time, if we're talking about cows, okay, if we're talking about cows, that's the question. We need some cow patty enlightenment here is the question. If we're talking about cows, then instead of t, I could put here x. And so x, this x would represent the time between one patty and the next patty. And what this says is that the distances between patties are, not times, distances between patties are exponentially distributed. So it's remarkable that you can come up with a simple mathematical model which produces the exponential distribution and has the property that it describes things as different, as diverse, as distances between cow patties and times between clicks on a Geiger counter. So the only requirement here is that in this diagram, when I draw these arrows, the arrow is just as likely to occur at one point as any other point, and whether or not an arrow occurs at any point is independent of what happened at any other point. And if I assume those things, and assume that there's a measurable rate at which these things occur, in the cow patty example, it's patties per unit distance. In the Geiger counter example, it's radioactive, it's clicks per unit time. But as long as I can measure that lambda, then these things would be described by an exponential distribution. Okay, so that, in my opinion, that's really quite remarkable. Yeah? Yeah, except that how do I know that the little f, that this density function means anything? It's exactly the same as the argument we made over here, which is I started out with this, but it didn't have any meaning until I got the distribution function, because the distribution function represents probabilities. Then I went backwards and said, yeah, but I could have gotten the density function by differentiating that, which means now that these things are equivalent, and once I understand it, I can look at a density function and say, oh yeah, as soon as I see some kind of rectangle, I know that I'm talking about a uniform distribution. But at the beginning, I don't want to just start out with that at a no place. The reason I wanted this is because it describes this, which is described by that. Okay, so now I could have started with this, but this is just arbitrary. So what I'm doing is I'm starting with a physical model which gives me this, and now I can say, okay, If that's the distribution function, if you differentiate it, you would get this density function. And if you integrate that, you would get that distribution function. So now I can look at this and say, oh yeah, that's an exponential. Let me draw the distribution function here. Let's see, I'll erase this. If I were to draw the graph that represents a distribution function, which is the cumulative area under the density function, so here's capital F. It's a probability, so it always lies between 0 and 1. When t is negative, it's 0. And then it's that exponential curve, which looks like that, and it's asymptotic to 1. And the derivative of that is that, and the area to the left of any point here is the height of that graph there. Now, any process in which the times between these arrows are independent, exponentially distributed, is said to be a Poisson process. This is very important. If you remember in our homework 1, we talked about the Poisson process. The formula that I derived using rate up equals rate down is valid if we have a Poisson process. And in your homework, we saw that because what you did was you generated the inter-arrival times using an exponential distribution. That's a Poisson process. And if you had a Poisson process, then everything agrees with the formulas, with the predictions. And if you don't have a Poisson process, then in general it doesn't. You need some other formulas. So the assumption of the Poisson process, it'll turn out, is critical to be able to derive the kinds of formulas we're going to derive. And now I've made the argument as to why those formulas are meaningful. Because the Poisson process, that logarithm that you put in your homework problem, that's not arbitrary. That's simply the way in which you generate exponential variables using the random number generator. So I haven't gotten to that yet. That's, again, the inverse transform method, which is covered in the earlier course, and I'll review that. The point here is that the Poisson process is the most reasonable, simplest possible process to describe events occurring randomly in time, and it's always one you would assume unless you have some reason for assuming something else. But unless there's evidence to the contrary, that's the simplest possible meaningful model. So it's going to turn out this is important, and that's part of it. Okay, let's calculate some of the parameters, some of the values for that. So any questions there? Okay. What's the expected value? Well, the formula is the integral from minus to plus infinity of the values the random variable takes times the probability it takes those values. That's the density function dt. So for this particular case, this becomes the integral from 0 to infinity. The reason the lower limit is 0 is because between minus infinity and 0, little f is 0 if it's an exponential density function. And then I have t lambda e to the minus lambda t dt. And now I have to integrate that. It turns out that the way to integrate that is integration by parts, but that's not important for our purposes. The point is now it's a straightforward freshman calculus problem, and so you evaluate the integral, and it turns out that it's 1 over lambda. So I'll just say integrate by parts. But I don't care about the technical details of integrating by parts. That's not part of this course. Okay, so the expected value of a random variable that's exponentially distributed, that is of a Poisson process, whose rate is lambda, is 1 over lambda. But that makes perfect sense, because if I tell you that cow patties are occurring at the rate of 2 per yard, then that means that the average time between cow patties is 1/2 a yard. So the average time between events is the reciprocal of the rate at which the events occur. Common sense. Likewise, if I wanted to calculate the expected value of the square of the random variable, then that would be equal to, by this same argument, t squared lambda e to the minus lambda t dt between 0 and infinity. And again, integrating by parts, the answer will turn out to be 2 over lambda squared, which means that the variance of an exponential variable is equal to the average of the square minus the square of the average, or in other words, 1 over lambda squared. So this is something that, just a fact which we'll may or may not use later in the course. Okay, any questions about this? How many people remember all this stuff, or at least it rings a bell? Okay, so there's not much new here. Okay, let me look at a property of the exponential distribution. So I think I'll erase this. Suppose I have events that are occurring according to a Poisson process, and I ask this question. Here's time 0, and I'm waiting for my first, I don't know, depending on what kind of person you are. If you are considering the subject, you could either use the example where you're waiting for your first arrival, you're waiting for your first Geiger counter click, or you're waiting for your first cow patty, whatever you like. So I'm waiting for my first cow patty, and let's say that right here at time y, nothing has happened. I don't have an arrow yet. And so I'm going to look and ask this question. Here's time y. Here's time y plus t. And my question is, what's the probability that x is greater than y plus t, given, that's a conditional probability, that x is greater than y? In other words, given that I've waited y amount of time for my first click and it hasn't happened yet, what's the probability that I have to wait at least t more for the next click? Okay, so I'm going to calculate this. And so the first thing to recognize as a review that this is a conditional probability. So as you all remember, the probability of an event E given another event F is equal to the probability of the intersection of E and F divided by the probability of F. That's conditional probability. So I want to apply that here. So the denominator is the probability of the event on which I'm conditioning. So it's the probability that x is greater than y. And by the way, I always use uppercase letters for the random variables and lowercase letters for the values that the random variable takes. Okay. So what's the probability that x is greater than y? That's the denominator. The numerator is the probability that jointly x is greater than y plus t, that's event E, and x is greater than y. That's event F. And now by ordinary logic, okay, so this equal sign is by conditional probability. And now by ordinary logic, you can see that the only way that x can be greater than y plus t and greater than y, it has to be greater than y plus t. So the numerator is the probability that x is greater than y plus t. And the denominator is still the probability that x is greater than y. Now, I haven't assumed anything about the process yet, but now I'm going to assume it's exponential. So now, right here, I'll assume that x is exponential. So the probability that x is greater than y is e to the minus lambda y. And the probability that x is greater than y plus t is e to the minus lambda quantity y plus t. And now by arithmetic, the numerator can be factored into e to the minus lambda y times e to the minus lambda t. Denominator remains the same. And then I can cancel out the e to the minus lambda y in the numerator and denominator. And I'm left with e to the minus lambda t. So the conditional probability that I have to wait at least t more, given that I've already weighted y, is e to the minus lambda t. Now there's something worth noting about that. Note that this answer doesn't have y in it. So in the case of the exponential, the y cancels out, which means that the length of time I have waited is irrelevant in predicting the length of time I'm going to have to wait in the future until something happens. In fact, e to the minus lambda t is exactly the same as the original probability that x is greater than t. So what we showed is if we have an exponential process, if we have a Poisson process, then the conditional probability of having to wait at least t more for the next event is just as if we were starting from the beginning, independent of how long we've already waited. That's called the memoryless property, or lack of memory property. Lack of memory, or memoryless. Memoryless, or sometimes often called the Markov property, after a mathematician, Markov, who either he was the first person to study this, or he's noted for his poor memory, or maybe some combination of those. I don't know which, but anyhow, this is called the Markov property. Now, this obviously is very important. Very weird at first. It's also very important. The reason it's important is that when we write equations in queuing theory, if the underlying variables are exponentially distributed, that means that the process has this Markov or memoryless property. That means that in representing it mathematically, I can neglect the information about the past history of the process except for its current state. So what matters is where I am now and not how I got there. It doesn't make any difference whether I have a certain number of people waiting in the queue and they've been waiting there 10 minutes or they just arrived now. If everything is exponentially distributed, if it's driven by exponential distributions, that means that I can ignore this information, and that makes everything simpler. And it'll turn out that's why rate up equals rate down works. It's so simple. It's simple because it neglects certain information. And to be able to do that, that means that implies that underlying this must be exponential distributions. And that means that in our rate up equals rate down, if we have Poisson arrivals and exponential service times, then we can write rate up equals rate down because those simple equations neglect things that it turns out are irrelevant. So this is going to give you some insight into this. Of course, there's a lot more to go. I'm just saying this in words now because the way to do this is to introduce these ideas and then kind of peel things away, peel back the onion, as I like to say. So we have this important memoryless property. So this leads to what's sometimes called the waiting time paradox. And this is going to be discussed in homework 2. So what I suggest you do, although we won't start looking at it right away, not in detail anyhow, but eventually I'm going to get to homework 2, and homework 2 concerns this memoryless property and the so-called waiting time paradox. So just let me briefly state what the waiting time paradox is, and then next time I'll go back to the this probability and go through the inverse transform method so that then you will understand exactly why it is that the simulation I gave you in the first lecture, why that in fact generates exponential inter-arrival times and exponential service times. So that'll be critical for the rest of the course. So I have to prove that theorem, which is something I've done in the stochastic models course. So those of you who took this course, that course, will recognize it. But one thing about that course that's different from probability courses that are taught in the usual standard way is they don't discuss that because simulation is not generally assumed to be part of elementary mathematical probability. In my opinion, that's a mistake because simulation is what makes probability meaningful, I think, to most students. Without that, they're just manipulating symbols. So that inverse transform method is very important, so I want to prove it again. Okay, but here is my waiting time paradox. So to make things simple here, let's assume that we have a process in which there are taxi cabs. And the taxi cabs, there's a taxi cab stand, and the taxi cabs arrive at random to this stand on average an hour apart. So the rate is 1 taxi per hour, but they arrive at random independent of each other. So every once in a while, there's a taxi, and then there's another taxi, and then there's another taxi, and so forth. And in this model, a taxi zips by the taxi stand. If someone's there, picks them up and goes away. If not, then the taxi just leaves right away. So the question is this. What happens is, on average, let's call these x's. So this is x1, x2, x3. Those are the time between taxis. And on average, the average time between taxis is 1 hour. So that means that the rate is 1 taxi per hour, because those are reciprocals of each other. And now what happens is that you arrive at some time t. It's your arrival time, at random, and you have to wait for the next taxi. So let's call this time here, typically it's called r for remainder, because what happens is you have interrupted an inter-taxi interval. And so there's a remainder, that's the remaining time in the interval. That's how long you have to wait for the taxi. And then there's an age of the interval. That's how much time has elapsed since the last taxi. That's the one you missed. And then there's I, which is the length of time, the interval between taxis. And of course, the I is one of the x's. In fact, the way I'm going to simulate this is I imagine that I have this urn. So this is the model of simulation. It has tickets in it. And the tickets the numbers are called x, and those numbers are going to be exponentially distributed because we're going to assume that we have taxis arriving at random. So I reach into here, I pull out the first taxi, the first number, and that tells me when the first taxi arrives. Pull out the next one, that tells me when the next one arrives. And in the simulation, you do this until for the first time you get a taxi arriving after time t. T is arbitrary. You make it whatever you want. And then you subtract that value from that value. That tells you how long you waited. You subtract that value from that value. That tells you how much time you missed the previous taxi by. And you know what the value of I is. It's the last value of x that you pulled out of the urn. Okay. Now the question is, on average, how long do you have to wait for a taxi? So what's the expected value of r? Excuse me. Expected value of x is 1 hour. That's by definition. What's the expected value of r? How long do I have to wait for a taxi? Yes. Okay. You say an hour because you took stochastic models. What I said. Okay. Anybody else want to take a different guess? Do so at your own peril because that's the right answer. But typically, okay, where we have more normal students, the typical answer is, well, you have to wait 1/2 an hour for a taxi because the times between taxis is an hour on average. We said so. So therefore, if you interrupt an inter-taxi interval at random, on average it should be 1/2 an hour that you have to wait. But the Markov property says it should have to wait a full hour. The reason being that according to the Markov property, the length of time from now until the next arrow is independent of how much time has elapsed and is just as if you were starting from the beginning. Okay, so what's the average length of time by which you have missed the last taxi? Looking backwards. So the ordinary student says, well, half an hour. But the Markov property student says 1 hour, because by symmetry, whether I look forward or backward, I should get the same answer. So if from here to here is on average an hour, from there to there should also be on average an hour. So then the question is, okay, how much time is there between the taxis? In other words, what's the average value of I? Well, according to the student, the answer is 1 hour. But according to the Markov property, the answer is 2 hours. 1 plus 1 is 2, because the expected value of A plus R is equal to the expected value of A plus the expected value of R. And if those are both 1, then the expected value is 2. Yes?
But isn't the expected value of I, just between any two taxis, actually the expected value of X?
That's the paradox. The ordinary student, the common sense answer says that, well, first of all, it says that the average value of the time between, well, let's see, the average, what the student says, common sense says that that the average time interrupted by the customer arriving is 1 hour, and the average time he has to wait is half an hour, and the average time he missed a taxi by is half an hour. That makes sense, except that it's not consistent with the Markov property. The Markov property says that that's an hour and that's an hour, but then by this statement here, the expected value of the time between taxis is 2 hours. So there are two possibilities. One is that the Markov property is wrong because 1 hour does not equal 2 hours. And the other is that the Markov property is wrong because it predicts that the value should be 1 hour here, whereas the student says it's a half an hour. So the question in the homework, at least part A of the homework, is to simulate this and to see what the values are. And of course it'll come out that the values are this, because that's what the Markov property says. But that leads to the paradox that how come it's a 2 when you said it was a 1? And so that requires some insight, some thought. So that's where we'll quit. You got a question?
Yeah, if you had never arrived, would it have been 1 then?
Yes. In other words, when you do the simulation, you'll see that when you add these things up, the average value of the x's is 1. Because in fact, you're making them that. That's the way you generate this. But when you actually do the simulation, you will find out that the Markov property, of course, is correct. It has to be. I proved it, which means that this amount must average out to 1, and this amount must average out to 1. And by this theorem, the sum of them has to average out to 2, and that says what's going on here, because I know I picked that value from this urn, and we know the average of the values in this urn is 1. So that's a paradox. Not that much of a paradox, because it can be easily explained, but it's something that's startling enough so that people don't realize this until it's pointed out to them. And that's part of the point of this course, is that you spend your life waiting in queues. You have no idea why you always pick the longest queue, why you're so unlucky. And you think that it's a curse on you personally. But what we prove in this class is that your bad luck is in fact an example of the curse on everybody. So that means that you shouldn't feel paranoid about it. You're just one of the people caught in the hurricane like everybody else. Okay, so let's see. Today's Wednesday. So we meet again on Monday, and then after that, I'll remind you about the following Wednesday, where we'll meet on Tuesday. Whatever it is, I'll let you know. Okay, see you on Monday. Okay.